All right, welcome. Starting a little bit late, it's okay. All right, so we're in chapter 6, and I know you guys are either going to take machine learning, or you are taking machine learning, or maybe you have taken machine learning, right? And so of course, we're just kind of scratching the surface. In fact, right, you might be aware that there are such things as bagging and boosting, and we're just going to focus on bagging. I know it's kind of funny terminology, but we're going to focus on bagging, and then I'll let Bevan teach you guys about boosting. But there's so many kind of things to pay attention to when you're boosting, and you get pretty much the same results, so or similar results usually. So then I don't want to take you down this path of all the things that you need to be careful with when a simpler method does pretty much just as well, right? And so we're going to focus on bagging. The textbook talks a lot about boosting and all the kind of ins and outs, so you can have a look through there. But last day we talked about, so just a little bit of review, and oh my gosh, I almost forgot. We have our test 2. Uh-oh. I know. What's the monkey that covers its eyes? Oh, I don't want to. In fact, I think that might be perfect. Hey, it was like ready to go for me. Oh, keep putting a period there. That's okay. Now, how do I make it bigger? Move this. Oh. That was worth it. I'll go back and remove that period, but test number 2 is supposed to be next Tuesday, but I wanted to check in with you guys and see if you would rather have it on Thursday or on Tuesday. So test number 2 is going to cover chapters, I think we did 1 through 3 for test 1, right? And so 4, 5, and 6. Right? Or never. What I am thinking, so just so you're aware, what I am thinking, yeah, never would be good, right? What I am thinking about doing is the same thing that we did for test 1, where it's just open for the entire day and it's a timed test, which you could use our class time to do it, but you don't have to, right? Because yeah, so let's do that. And then that way, you know, if you're dealing with time zones, and you can kind of be a little bit more flexible. So it'll be a timed test. So you'll have 1 hour and 20 minutes to do it. 1 hour and 20 minutes, right? Open from well, technically 12:01 to 23:59, or I should say 001. I'm just trying to emphasize that it's all day. It's really hard to be clear, I guess. But so open from midnight till midnight, and I haven't really gotten okay, so the options are either Tuesday or Thursday, because of course I want to use a day that we have a class on. so that you can have that kind of scheduled time if you need it, right? But I don't know. Where are we here? I feel like I had it for Tuesday. Tuesday, yeah. But we could do it on Thursday. Thursday? That's the only vote I've gotten so far. Not Tuesday, Thursday. So I'll switch those around. That means that we're going to start chapter 7, which is not on the test, but you can keep track of that. That's okay. Or it kind of gives me more time to finish up chapter 6 if we need it, right? And so so that might be nice to have as an option. I've given ourselves I've scheduled 3 days for chapter 7. I think we only really need 2, but it might be nice to have kind of some downtime. Okay, so the assignments are going to be good practice, and just like the last one, right? I'm going to make it a little bit harder because you guys did really well on test 1, so I need to make it a little bit harder, but not too hard. I don't like to make them too hard. Okay, so the assignments will be good practice for the test. Okay. Good. So we'll put it on Thursday, which means that there's no we won't meet. We will not meet on Thursday. Oh, I'll give myself a little bit more room here. You can use the time to write the test if you want to. Yeah. So kind of the same situation as test 1. Then, so there are numerical questions, right? So the assignments, we've incorporated reading some output and doing some calculations, right? A little bit harder than test 1, which was really just definitions, right? And so put you through the ringer. There will be some definitions here, but yeah, so Thursday, I guess I should put a date. What is the date for Thursday? April 7th. So I'm going to change that on our Moodle page. Oops, April 7th. Yeah, fire up those R's. Yeah, get them going. I don't want you to have to use R under pressure, because that's not how coding works, right? Coding is, you sit down and you work through a problem and you try stuff and you kind of try to work it out. So what I'll do is I'll give you output and get you to use it. Yeah, so yeah, so you don't have to generate a PDF or anything. It's just going to be just the answers that you give me. I'll give you a Dropbox where you can upload your written work, but all I'm expecting is maybe, handwritten work that you've scanned and uploaded, which we did in Stat 230. So but that's just as kind of insurance, right? If you find that, oh, I entered that wrong, but I did it right in my work, then you can tell me to go and check it out, and then I can have a look. Okay. So it'll be optional. Okay. So, all right. What did we talk about last day? We talked about K nearest neighbors. So in terms of review, we talked about K nearest neighbors, KNN. Right. And what we decided was, okay, it's a relatively simple thing that we could do, right? If we have some distance metric that tells us which observations in the data are close to the one that we're interested in, right? So what makes a neighbor is being close, right? And so if we have some way of measuring that distance, which we do, right? We talked about the Euclidean distance. There are others, but the default is the Euclidean distance, and maybe the Manhattan distance comes up every now and then. But those are the two main ones, right? And so if you have as a default the Euclidean distance, that's great. So then if we are able to measure the distance between the values that we're interested in and the values in the data, we can find our closest neighbors. And then we can look and we can see, okay, what was the outcome for those neighbors? And if I'm doing a classification, I might do a majority rules, right? So 13 out of 15 were ones. So I'm going to classify this as a 1, right? I'm going to predict that this is going to be a 1 as well, right? There were 2 that weren't ones. So there's a chance that I'm wrong, right? But in general, right, we just go for majority rules for classification. Or if I am looking at a numerical outcome, then I might take the average of those outcomes, right? My nearest neighbors, my 3 nearest neighbors, or my 5 nearest neighbors. So notice that you can play around with your K to get different predictions. There's kind of a trade-off. You don't want to go for your first nearest neighbor, because then you're losing a lot of sample information. But you don't want to consider 20 neighbors, because that might be a huge amount of your sample. And so then you're looking at too many neighbors, you're kind of going too far. And so you want to have like a trade-off. So usually you look at a couple of different Ks and see how your model performs. Okay. And how it performs, how do we measure that? Well, we can look at some test set that we have and apply our model to that and see how it does with predicting or classification. So what we said was, okay, K nearest neighbors, we can use it kind of in 2 ways, right? So the first way is just as a way to classify or predict an outcome. Okay, so we can use KNN in 2 ways, right? One relies on the first one. The first one is just to make predictions or classifications based off of the neighbors, right? So make predictions or classifications based on the neighbors. Yeah. Or we can take it one step further, and we can use those predictions or the classifications, and we can use those as what we call a feature engine. Or rather, we're generating features, which we've been calling predictors, right? So the second thing that we could do is we could use these predictions or classifications, right? So use the values from 1, right? So now we're going to use those values as predictors or features. as predictors, or maybe I'll say as a predictor slash feature in a different model. Okay, so usually you wouldn't really want to use k nearest neighbors and use it in a k nearest neighbors again, because then your prediction, you're kind of inbreeding your predictions. You probably could, but I wouldn't want to do that. It makes it hard to explain too, right? And remember, that's part of our job, is to explain what we did. So I'm constantly trying to figure out, okay, well, what's easy to explain? What do I feel like explaining, or how much do I feel like explaining? And that's basically how complex you can go usually. And so you can use those values in a linear regression, for example, or maybe a logistic regression, right? So some other model as a predictor slash feature in a different model. We've talked about multicollinearity, where the issue becomes if I have redundant data. So if I have a variable A and a variable B, and then I have another variable which is essentially 2 times A, that's redundant, right? I don't want to have A and 2 times A in there, because then I have that same information and I just have kind of a parallel information in my model. So then it's going to give me an error, it's not going to run, and it's because I have that redundant information. The difference between using k nearest neighbors as a predictor or as a feature, I'm trying to use the term feature, but it's hard because I'm so used to using predictor as my X, right? So here, really what I'm saying is as an X, right, in my model, right? X1, X2, X3, X4, or an explanatory variable if you prefer. Shoot, I was talking about something. Oh yeah. So it feels weird to incorporate the values or the average, let's say, so the average sale price for my 3 nearest neighbors, right? And not necessarily geographically, but usually, right? But it's not looking at the average of the entire data, and it's not looking at, those exact values. So there is no multicollinearity, because each observation is going to have different nearest neighbors. So if we're only looking at the 3 nearest neighbors, then we're safe, right? We're not looking at the entire data. We're just looking at those 3 nearest neighbors, and that's going to change for each observation, right? So there won't be an issue with multicollinearity, even though that feels like it could be in the beginning. But I'm here to tell you it isn't. Okay, great. So that's what we talked about, and we spent, a fair chunk of time talking about it, because it is, a kind of a big thing that we could do. Yeah. The other big thing that we could do are decision trees or trees. Okay, and so tree models or decision trees, we can call them decision trees, but sometimes that means something else, but relatively similar. So we could call them decision trees, but usually we call them tree models. That's not for you to worry about, but it is something. Okay, so tree models, you have probably seen tree models. We usually draw them out. Now, so what we do is the model or the algorithm goes through the data, and it partitions the data into the most similar groups. So you start and you have nodes that separate the data. So each node is going to give you some decision value, I guess, right? So if, for example, if we have gender in there, right? If the gender is male, then you go down this branch, right? Or if the gender is female, you go down this branch. If that's something that separates your data, right? And so, for example, if we go back to the real estate data, right? If this is a house, then my predicted price might be different than if I have a condo with the same attributes, right? Even if it's, you know, a 3-bed, 2-bath house versus a 3-bed, 2-bath condo, right? My predicted prices might be different, right? And so what it tries to do is it tries to lump this all the similar observations into little groups, and so we keep divvying up the data until we have it so that we have this decision tree, and then we're able to make classifications usually, or we could predict things like the sale prices, but usually we want to predict a binary or categorical outcome. Okay, so tree models in fancy terminology recursively partition the data. Recursively just means that it goes through and then it starts over again, right? So we work recursively, and I'm trying to remember the difference between iterating through and working recursively. I'm sure there's a subtle difference, but I think the terminology can maybe be used interchangeably. But anyways, recursively partition the data into increasingly homogeneous groups, so similar groups, right? And so we've seen the nearest neighbors, right? And so those are similar observations, right? And so they kind of go hand in hand. This is just another way that we can do it. And so we recursively partition the data into increasingly homogeneous groups, and homogeneous is so long that I'm gonna genius groups. Started on a new line. Right, and so homogeneous means similar, right? Homo is the same, and then genius, I think, is the genus, but I'm not sure. I love working with etymology. Etymology is like where roots or root words come from. And it tells you a lot about the meaning of the words, right? And so, so for me, right, homo means the same, and then so the similar groups, long word to spell, okay? And so it goes through and it says, okay, my first partition, I can see that I have these two obvious clusters that look similar, and so that's my first split. Then I go in and I focus on each of those clusters and I say, okay, I can kind of tease you guys apart based off of maybe your credit score or something like that, right? So some observation in the data, right? I can tease you guys apart, and then I go into my other cluster, and then I find, and it could be a different criteria that I look at, right? So maybe your age for this cluster. Okay, this cluster I can separate by age, right? And then I can make them more similar. Okay. And so you go through and then you go back and you go into each of these. Now you have 4 clusters, right? Potentially. And you keep going until all the groups are similar enough, right? And so how do we measure similarity, right? Just like we had to be able to measure distance, how do we measure the similarity or this homogeneity is through impurity, right? So if we make these divisions, right, we use our data to construct these divisions. But what if we apply it to new data, right? Then I'll be able to figure out, or I'll be able to look at my data and see how it behaves and whether I was right or wrong in my classification. And then I'm going to have some misclassification information. Okay. And so we measure homogeneity by impurity. Okay. So impurity means, okay, so once I applied these decision rules to new data that I didn't use to build these decision rules, then how many were misclassified, right? And so impurity relies on the accuracy. Okay, so impurity relies on the accuracy of our tree model. Oh, accuracy of our tree model. Okay, and so the accuracy is the proportion of misclassified records. So P is going to be the accuracy, which is the proportion of misclassified records. So each cluster is going to have, or at each node, you're going to have some accuracy measure, right? So one of the problems is that we build these decision rules based off of our sample, and then we go and we try to take those decision rules, and now we try to apply it to new data, right? And so it's going to be perfect for our sample, but then when we take it to our new data, right, there's going to be misclassifications, and that's okay, right? But the accuracy is how many misclassifications did we have, right? And so the impurity relies on the accuracy, which is this P, okay? And so the simplest method that we could use is just kind of randomly assigning a classification as a 1 or a 0, right? So, oh, okay, you're a 1, you're a 0, you're a 1, you're a 0, you're a 0, you're a 1, right? And so what would our accuracy be then? Predicted would be 0.5, right? And so P equal to 0 is a perfect classification. Whereas a P equal to 0.5 is, well, it's the worst classification. It's just randomly assigning them, because remember, P is the proportion of the misclassified. So it's the number of misclassified over the total number classified. And if we only have two outcomes, 0, 1, then I'm expecting half of them to be zeros and half of them to be ones, right? And so that's where this 0.5 comes from. Right, and so this is the same as randomly guessing, which is a bad classification. So of course, we're aiming for a P that's close to 0. We understand that it's not going to be 0, right? But we're hoping for something close to 0, right? So want P close to 0, right? Or as close to 0 as we can, right? We want to move away from just randomly guessing, because then why did we build a model if we can do just as well by randomly guessing what classification it is? That doesn't really make sense. And so we don't just look at the accuracy. Remember, we talked about sensitivity and specificity and precision, and off the top of my head, I can't remember what they all are. Sensitivity is the ability to pick up true ones, I think, and specificity is picking up true zeros. Hey, this isn't for me to remember, this is for you to remember. Anyways, you're all working open books, so make sure that you have those and you have them organized somewhere, because they are impossible to keep track of. I shouldn't say that, but they're tricky, right? So just keep that in mind. So same way that we didn't really look at accuracy as a raw measure, because especially if we have rare outcomes, then our accuracy might be high, right? Because if we just let everyone be zeros and we only are expecting to see a couple of ones because they're so rare, right? Those ones would be misclassified if we just let everyone be zero. That's one way of doing it. Our accuracy might be really high, but none of our ones were predicted correctly, and that kind of defeats the purpose, right? And so same idea, right? We don't use the accuracy itself. We measure something called impurity and sensitivity. Sensitivity is the recall, which is the proportion of correctly classified ones, I want to say. I'm trying to remember what the page looked like. Okay, and then the specificity. It's in the textbook. It's in our notes somewhere. I'm feeling pretty confident though. I'm curious to check it, but anyways, you guys can check for me. Okay. Nice. So instead of just measuring, hey, that's a good question. So is impurity something that we only use with tree models? I think so. You could probably use it with clusters. I feel like you could apply it to something other than just tree models. A lot of what we're going to do is tree models. Nice. Okay, so sensitivity is the percentage of true positives, and specificity is the percentage of true negatives. But that's a good question about the impurity. Can we use it for something other than tree models? My answer is, I don't know, but I think so. I think we could use it for other models. I guess we'll find out. No, I'll have to do a little bit of research. That's all right. It seems kind of generic, so I feel like it probably came from something else. A lot of this, machine learning stuff comes from more kind of rigorous statistical analysis, and so I feel like it's based off of something else. Yeah. So as soon as we got these clusters, then we're going to have impurity. So I'm willing to say, yes, we can use it for other things. But what is impurity? So, okay. I guess we'll see. We'll see. I feel like it comes up later in chapter 7 as well, but I don't want to commit. Okay. Yeah, I think I'll let you guys talk about data science 400. I don't even know which one that is. Anyways, I think Well, I know you see decision trees just briefly in Data Science 300 at the very end. Yeah, which is data wrangling, which is a weird name for it, but whatever. Okay. Impurity. There are many different measures of impurity, just like there are many different measures of correlation, but there are kind of some that we use and kind of rely on, and then we kind of, there are others, but just like the distances, right? We focus on the Euclidean distance, and we're going to focus on the Genie impurity. I think it's pronounced Genie. I never looked it up, but I prefer to call it Genie because it's so cute. It's like Genie in a bottle. And so a common measure of impurity is the Genie impurity. Right, and the impurity of some data A or some cluster A, and that's not important, is going to be P times 1 minus P, right? So instead of just relying on the accuracy, right, which is P, then we also take into account 1 minus the accuracy, which is kind of the opposite of accuracy, wrongacy? No, something like that, right? We've got the complement. And so here, right, this is the accuracy and kind of the opposite of accuracy. All right, so we don't want to just focus on the accuracy because it might not tell the whole story, right? But that's a really easy way to measure impurity, is P times 1 minus P, and that's easy to find, right? So computationally, it's very, very cheap, okay? And so that's a good thing. And so that's the one that we're going to stick to. They also mention the entropy information, which is a little bit more advanced, right? So we could use the entropy information. Which had kind of a, so the impurity of A, which is just the cluster, let's call it, was negative P, and I'm copying this from the textbook, negative P times the log base 2. Log base 2, that's weird, right? We usually use log base E, right? Whenever you just see log, especially in a stats or a data science textbook, they mean log base E, the natural log. Okay, so log base 10, that's for, I want to say, physics and light and kind of sound waves and stuff. That's not what we're dealing with. So log base 2 of P minus 1 minus P times log base 2 of 1 minus P uses a lot of P's, right? And so here we've got the accuracy again, and it's some version of P and 1 minus P, right? And so it's just a little bit more complicated. Not something that you would calculate by hand anyways, right? You would make R or Python do it, but it's good to know where it came from, right? So most of the time we're going to be using the Genie impurity. Maybe I'll use square brackets. So it's a little bit more pronounced here, that this is kind of optional. I will focus on 1. Right, all we need is 1 to get started, right? We only need 1 type of impurity. We only need 1 model. We only need one way to do it, and then we can build off of that, right? And I guess I've taken the same approach for bagging and boosting, which are both going to use tree models, right? And so we're just going to build more than one tree model. So they both do the same thing, but let's focus on bagging, because if we can do bagging, then we can go a little bit harder and we can do boosting as well, right? But we need to know how to do one before we can do the other. And again, not something that you're going to do by hand, obviously, but things that we need to know. All right. So this tree, if we let it run wild on our data, right? So the training data that we're using to build this tree, right? It's going to get down into the very nitty gritty and potentially separate two little responses from each other based off of some criteria, right? And so really what we're doing is we're overfitting this tree, right? We're letting the tree just kind of grow and grow and grow and grow until those decision rules are very, very specific to the data that we're training on, right? And we don't want that, okay? Yeah, exactly. So you're going to overfit the data. So I want to write down what I just said. Okay, so our tree will grow and grow and grow and grow. Right? So our tree is going to grow and grow and grow until all the different clusters have been identified, right? Until all the similar groups have been identified. Have been identified. Okay. This could go as far as creating a cluster of size 1, right? A group of size 1 at the end of each of your trees. So typically, although trees, real trees, let's get back to real life. Real trees start at the bottom at the root, and then they grow up like this. But how we read decision trees, so usually we start here at some node. So this is a node, which is also the root. And the root gives us our first decision, and then that splits our data. Okay, so maybe if the credit score is less than some number, right, then I'm going to put you in this group. If it's not less than that number, then you're going to go in this other group. And then we kind of zero in on different attributes. Okay, and so each of these are going to end up in a node, right? And then so what happens is you can keep splitting, and sometimes if this group is completely homogeneous, right? The impurity is 0. Is it 0? Yeah, because the accuracy is 0. There's no misclassified values. Whew, terminology, right? And so no misclassified values here, then and all of these guys are all the same, then we can stop growing that, but we can keep growing the other nodes until things get out of hand, right? And you can kind of keep growing and growing and growing until potentially everyone has their own leaf. So this is what we call a leaf. Right, and this would be a leaf. And at the end, you have all these different leaves. Can't really see that that's the root, but this is called the root. So the root node. Yeah, and then so decisions are being made based off of the features, I wanted to say predictors, but the features in our data, right? And so our tree is going to grow and grow and grow until all the similar groups have been identified, right? This could end with each response or each observation as its own leaf, right? With each response, or sorry, I'll say observation, with each observation as an individual leaf. This is the equivalent of overfitting, right, to this data. This is the equivalent, or it is overfitting, but we're used to it being, you know, we build a linear regression and we just have all these predictors in there, and it does so well because we have all these predictors in there, and all those predictors are contributing to predicting the sample, the data that we're building it off of. But then when we go to apply it to a different set of data, it's not going to perform that well, right? Because we've trained it so much on that specific set, right? So this is the equivalent to overfitting the data, right? So what we do is we can set things like the complexity of the tree, which really just limits the growth, right? So if you find that at some point you reach, maybe you don't want to exceed 9 leaves, right? Or something like that, right? You can set these different parameters, or they're called hyperparameters, that'll help guide the model, and it'll stop it when it gets too nitty gritty, right? Because let's see here. We often want to stop this this tree from growing, right? Or we could grow it and then we could prune it back. So it's kind of fun because you use all this terminology that we would use for a regular tree, right? But now we've got this kind of stats tree or data science tree, right? But same terminology applies. And so we often want to stop our tree from growing right? So that it doesn't become too training model specific. So that it doesn't become too training model or training data. Oh, that doesn't say training data specific, right? We want to be able to apply it to a different data set and still have it perform relatively well, right? And so usually we'll stop the tree from growing, but another way that we could do it is, or we could let the tree grow, right, until it's finished, until it is finished. Then prune it, right, until we have kind of a more general model that'll apply to different data. Then prune it. So really what that says is then you would backtrack these two and say, okay, that got a little too specific to this data set, so I'm going to prune it back and I'm going to end here instead of letting it split into 2 leaves, right? And so depending on what your criteria is, then you might end up pruning all the way back to maybe just the second node or something like that, right? depends on the data, so it's hard to say how many nodes you should have or how many leaves you should have, because it totally depends. It depends on what? It depends on how similar your observations are, right? Are they easy to figure out what the similarities are, or is it really hard to figure out these similar groups, right? Or we could let the tree grow until it's finished and then prune it until it can be applied to a different data set and perform approximately as well, until it can be applied to a new data set and still perform relatively well. That's always our problem, right? Is okay, we use data to fit these models. We have these models that learn from the data, right? So then everything that we do depends on the data that we have, right? And so it's always going to perform really well on the data that we built it off of, but how we judge it is by how well it performs on new data, right? So that's always our problem, right? And so some ways that we get around that is we don't report how well our model fits our current data, right? We split up our sample and we have kind of training data, and then we have some validation set that we apply it to. And then those would be the values that we report, right? Because they're going to be lower, but they're going to be more true, right? Okay. Okay. So we want to stop our tree from growing, and there are a couple of things that we could do. So one of the things is we could prune it back, or if we want to stop it from growing after it reaches a certain point, maybe a certain size, we can set that as a complexity parameter in R or in Python, right? And so here we can set this, only because I forgot to mention it there. We can set this as a complexity parameter in R. Oops, that doesn't look like R. In R or Python, of course. Okay. So one of the ways is we can limit that complexity. I want to say complexity, but it's complexity of our tree, right? Which really means, okay, how big is my tree? How complex is this thing, right? Is it easy to read, and is it easy to deliver to a client, for example? Okay, and so one of the things that is really, really nice about only having one tree, so one decision tree, is that that's something that you can include in a PowerPoint, and you can easily kind of hold your client's hand through your decision tree, and you're able to say, okay, if they are over the age of 30, and people can wrap their head around it, right? We're really decent at understanding if-then statements, right? So if they're over 30, right, and they have more than 2 kids, and they have, you know, this, that's who you should be lending to, for example, right? So we're able to divide up our population into these very specific groups, right? And that's easy for our client to wrap their head around, right? So it has that benefit of we can actually draw a tree and we can walk through those decisions, right? And so a tree model is a nice tool for us to have, because it's the easiest way that we can visualize these classifications, right? So a tree model is a nice tool to have, since we can easily visualize and explain right, how classifications were made. How classifications are made. Trees typically deal with kind of categorical outcomes, specifically 0, 1, so binary outcomes. You can use trees to predict numerical outcomes as well, okay? But then you'd have to adjust your impurity, right? What's your impurity? It's the accuracy, so it's the number of misclassified outcomes, right? But if we're not classifying anymore, then we have to be able to measure impurity some other way. So then we rely on the squared deviations, right? Just like we did for regression, right? And so a tree can also be used to predict continuous values or numerical values. So continuous values, right? So numerical, as opposed to, as soon as we say classifications, classifications are for typically binary data, right? Or categorical data. So a tree can be used to predict continuous values where the impurity is going to be, where the impurity is measured in squared deviations from the mean. Deviations from the mean. That's a little bit harder to wrap our heads around, right? So each group, if we divide them up based off of some criteria, right? And that criteria can be categorical or numerical, rather, right? Age, for example, height, whatever. Right? We could use those to divvy up our data, right? But if what we're trying to predict is numerical, then that's what we're talking about here. Then each group is going to have some mean and some standard deviation. And so then we can measure the impurity of how close together these things are, right? By taking the squared deviations. Deviations from the mean is really just the observation minus the mean, right? And then if we square those, then we have some measure of impurity. But you can see how it gets a little bit harder to talk about, right? It's harder to explain, okay, squared deviations from the mean, whereas misclassifications, okay, I applied this model and I found that 4 out of 5 were correctly classified. That's pretty good, right? Maybe. Maybe not. That means 1 out of 5 were incorrectly classified, right? And so so then I can use that as my impurity measure, right? Okay, so so like we said, a benefit with just having one tree is that it's such a nice tool to have to be able to show to your client, and it's easy to explain. But we also know that, okay, well, what if I looked at many trees, right? And what if I did some sort of weird average of those trees or something like that? I am going to get a better estimate, right? And our goal at the end of the day is to have a better estimate, right? So a better classification model or a better prediction model, right? And so, of course, we're going to build not one tree, but many trees, making what? A forest, right? And so, all right. So all the terminology, oh, okay, here we go. Right, so there's going to be benefit to fitting more than one model, but what happens is, what's that saying? You can't see the forest for the trees, right? The trees are in the way because so you can't see the forest. And so kind of the same thing happens, right? When we just have one tree, it's so crisp and it's so clear to look at it and see exactly what's going on. But then as soon as we say, well, we did 20 different trees, and then we did an average at each node, and we just kind of did a mashup of all these trees together, that's really hard to explain all of a sudden, right? So a single tree is easier to explain. And I'll put in brackets to a client because of course that's what we're dealing with here. To a client, boss, stakeholder, whatever, right? And so it's definitely easier to explain to a client, but considering multiple trees, yields superior predictive accuracy. I had that written down, so I wanted to say it just like that. It yields superior predictive accuracy. What's one thing that you could consider, right? What if you built multiple trees so you use these more complex methods, right, that we're about to talk about? So random forests, bagging, maybe even boosting if you're comfortable there, right? What if you use these more sophisticated methods and then compared it to just a single tree that you've built, right? If for some reason those more sophisticated methods don't give you superior predictive accuracy, then you would opt for that simpler one that you could just give to your client, right? But then you'd also be able to say, okay, and we looked at, you know, these more complex models, but this one performs roughly the same, right? And so that's a selling feature too. We're always going for simplicity. We explore the complex and we explore all these hard things, and that's our job, right? But if we're able to present a simpler model or a simpler solution, then that's good, right? So that's something to kind of keep in mind too. Okay, so a single tree is easier to explain, right? But usually we end up having to consider multiple trees. Okay. So some of the things that we could do, three common methods we can use, methods of considering multiple trees are: one, bagging. I feel like that's where it doesn't have that kind of tree analogy, and it's probably because it doesn't necessarily mean trees. So bagging and boosting and, well, random forests have to do with trees, but I think you could probably do it with other models as well, right? So it's not necessarily tree specific, although random forests are. So bagging, random forests, and boosting. We're going to focus on these. So we will focus on these. Boosting, we'll talk about boosting. And of course, like everything, right, there are different ways that we could do bagging. There's different ways that we could make random forest. There's different ways that we could do boosting, right? So of course, there's kind of subcategories in here, right? Everyone had to get their PhD somehow, right? Oh, I did bagging, but with a tweak, right? And you can see how that's how these things go, right? Oh yeah, I did boosting, but I just made this one change and now it's my way of boosting, right? So then everyone has their own way, right? And so just makes for more for us to learn about, right? But in general, we'll talk about them. So we're going to focus on the first two, and then we'll talk about boosting just briefly. Okay. There was something I wanted to say about bagging before I actually went into it, but that's okay. I can't remember. Okay. So, bagging. Bagging, the term comes from bootstrap aggregating. Aggregating means putting together, right? Which brings us back to ensemble methods, right? Where we're putting together different methods of predicting things, right? And so it all kind of ties together, but it comes from bootstrap aggregating. And so remember, we talked briefly about ensemble methods, and ensemble means together, right? And so we put these things together, and we have different models that we put together, and we leverage how they work together. Okay, and I think I mentioned the Netflix prize at one point, where Netflix offered $1 million if you could increase their predictive accuracy, right? And so I think what they said in the textbook is they ended up using an ensemble of all the models that were doing well, right? Because then if you run all these models and then you take, the average prediction or the majority classification, right, then you have a stronger model, right? This kind of army of models is your ensemble that are working for you instead of just the one. Okay, and so bagging is the same thing. So it's an ensemble method. Okay, but what happens is we change the data by bootstrapping. So remember, bootstrapping is when we kind of generate data from our existing data. And it sounds weird. It sounds like it wouldn't work. It sounds like it's hokey, but we randomly select an observation from our sample, and then I use that, and then I put it back in, and I randomly select another observation from my sample, and I have some specified sample size that I want out of my original sample, right? And because they can be resampled, right, I can generate a larger data set than I actually have, right? Or I could just take a random sample of my sample and use that as my training data, right? But that leaves a chunk of data that I haven't used that I can use to check my model against, right? So there's benefits that, and that's the bootstrap. So it's the ensemble method, but each new model is fitted or fit. Let's say fitted, I don't know. Is fitted to a bootstrap resample, right? Something makes me think that they're using without replacement, because then they randomly select from your sample and you have your training data, and then you have also generated a test set, right? So a validation set that you can check against. So I didn't write anything down about that, but I think it might be without replacement. So I'm not committing either way. Something to look into. So it's an ensemble method, but you fit it to a Bootstrap's resample. Okay, and so then what we call the bagged estimate is the average of the models. So each model is going to give you some estimate, right? And then once you put all your models together, then you can take the average, and that's going to be your bagged estimate, right? Bagging. Put them all in a bag. Okay. I think I'm kind of running out of time. So I'll save some of this, the random forest, and a little bit of boosting for Tuesday. And then that might be nice, because then we have the test on the Thursday, and then we don't have to rush through things before the test. So we'll stop there. If you have any questions, let me know. Otherwise, I'll post a lab for tomorrow, and then I'll see you on Tuesday. All right. Thanks, guys. Stop this recording here.